Welcome everyone. Thanks for joining us. Today we are very excited to dive deep into the depths of Delta Lake 4.0. Before we begin, let us take a moment to introduce ourselves.
Hi everyone, I'm TD. I have been involved over the last 14 years in the Spark side of Spark, Delta, big data side of things. Till 5 years ago, mostly in Spark streaming, over the last 5-6 years, specifically in Delta. So yeah, really excited to talk about Delta 4.0.
I'm not a celebrity like him, so don't expect much. I lead the storage efforts in Databricks. I work on a lot of storage related things. Primarily, like the stuff that my team works on is Delta and lots of things related to Delta. You might have heard a couple of things pop up in the keynote and whatnot. So, liquid predictive optimization. We also manage the open source side of Delta, the ecosystem side, interoperability, and there's like a whole laundry list essentially. So feel free to catch us after the presentation if you have any questions.
Just to be clear, he is my boss. So if I make a mess, I'm getting fired today.
Or more, it's the other way around. He's the guy who gives me the hard time. I know most of you came back from lunch, so perhaps let's start with a simple trivia. Any wild guesses to this particular question? You can shout it out. This is a quick sleep check to make sure you're not sleeping. Any guess? One guess and I'll move on, otherwise you're going to watch me here on stage silent. Lakeview? Unstructured data? Okay, here's my answer for this. Never said it's going to be funny, I just said I'll wake you up from sleep, essentially. So.
You have to groan louder.
Let me start with a couple of numbers around Delta Lake. I think you've seen some of the numbers in the keynote, but if not, I'll also explain my perspective on this. This number of 4 exabytes has pretty much taken me by surprise a few days ago when we were doing analysis on what's the amount of data that Delta kind of passes through every single day. 4 exabytes and 1 billion clusters per year utilize Delta. I could not get that number sink in, so I was trying to understand okay, what exactly does this number mean? In fact, this is a 2x growth compared to last year. And the best way I can explain this number is, if you take every single human on this planet and ask them to watch the #1 popular YouTube video, which is Baby Shark, don't ask me how I know that, and they need to watch it 5 times a day, that's when you're going to hit this 4 exabytes number. It took a while to kind of sink that in. Beyond that, I think it's pretty humbling to kind of know the amount of love that Delta actually gets. More than 60% of the Fortune 500 companies rely and trust Delta. There are over 10,000 companies. I think you saw some of the numbers in today's keynote. It's about 12,000 now. They use Delta in production. We have a constant barrage of features coming in, thanks to all of you. This time the count is about 80 plus, essentially, this year. And we have a very large growing ecosystem of developers contributing to Delta, in fact. It's pretty fantastic. Over the years, the growth has been nothing but stunning. Just to talk a little bit more about the community, we have about 11 repos in the project. In fact, the really cool thing is, this is the Delta side of the talk. There's a Rust side of the talk going right opposite to this door as well. Shameless plug. We have a lot of incubator projects also going on. There are more than 50 releases. The community is super active, and let me show you some numbers. This is the accumulated stars across all of the projects that's going on. It's pretty wild for a niche project in the data space. More than 500 contributors. Slack has amazing things happening all the time. We invite you to kind of come in, talk to us on Slack. We're very, very active on Slack. LinkedIn is also a growing community of users. YouTube is something that we are picking up right now. We're putting in more than ever, tutorials, talks and everything, so catch us online there as well. This kind of growth is something that we've never really anticipated. Over the years, Delta has grown quite a bit, And more and more recently, we've been having a lot of query engines like Druid, BigQuery. They've also started adding support for Delta, which is a testament for the technology itself and in development within the community. So before we begin and get into like, hey, what's coming inside Delta 4, let me actually focus a little bit on what happened in the last year or so. For those of you who have not really heard of like Delta 3, or you don't know like, okay, what's going on? Like, why am I talking about some of the stuff in Delta 4? I think a little bit of context will actually go a long way. So let's revisit a few problems that Delta 3.x was trying to solve. The top challenges that Delta was trying to solve were multifold. I think there's like this whole matrix of things that are here, but I'll focus on a few key things that will hopefully convince you in terms of the direction that we're actually taking. Small merges on big data is pretty much like a butterfly effect. You could be a small user like trying to do your thing, updating one row, but then you wouldn't realize that it's happily launching out a job that is going and rewriting terabytes or petabytes of data behind the scenes, in fact. This is a pretty big problem to solve, and this is one of the big reasons why we introduced something called deletion vectors very recently. The idea behind a deletion vector is you have this operation called upsert. Upsert is a simple operation. You want to change something in your data, but the problem is most of the data lakes or the object stores that are that we use underneath are immutable essentially. So you'll have to figure out a way to convert this operation into a delete and an insert, which is what deletion vectors actually does. So conceptually, it's super simple. So if you were to take an example, imagine you have a Parquet file and you want to update one particular row. What ends up happening is, we don't really copy that file anymore. Nothing is done to that original file. If it's a gigabyte, we don't really do much. We just capture that there is an update that was made into that particular file in a different file. That file is called a deletion vector. That's all you need to know. The complexity here is in the mechanics of how this is actually implemented. So internally, if you go through like some of the Delta code base and whatnot, you'll see that we use compressed bitmaps in order to represent some of this stuff. It's pretty fun stuff, essentially. Like, I highly encourage you to look at it. And the challenge was, it's not about implementing deletion vectors, it's about implementing it correctly, in fact. So on the left side, you see here a graph. On the x-axis, it shows the number of rows merged. And on the y-axis, it shows the duration in which we finished that operation. What you'll see is, on the left side, you have the merge performance with deletion vectors. So when you execute a command like upsert, what is the amount of time it takes? We see almost like a 3 to 4x improvement compared to the classic merge that Delta initially had. But the really cool thing is the graph on the right side. The graph on the right side, when you put it together with the one on the left, it shows that there is no penalty on the read side when you do adopt deletion vectors, which is really fantastic, essentially. And we've heard a lot of users be super happy about it, to the point that now there is a very broad ecosystem of people who have already adopted this. And this has been a very big surprise to us, essentially. The players like Trino, BigQuery, DuckDB pretty much adopting some of this stuff is quite encouraging. And we've actually done this fun math. There's been about like 100 trillion row rewrites avoided just because of deletion vectors, in fact. Like, it's pretty fun stuff. The second challenge that Delta 3 was trying to solve is partitioning. When it came out, the idea was so amazingly brilliant. Use folder names to start doing data skipping and data pruning. It was fun while it lasted. The problem starts when your workload patterns start changing. You don't know what you're doing. You pick the partition key with like a lot of cardinality. Things start breaking down, essentially. Towards solving this problem is why we started liquid clustering. The idea is pretty simple. From partitioning, just switch to using clustering. And this clustering technique is pretty much flexible in the sense that you can define it at the time of the table creation. You can choose to change it any time without any rewrites. Only the new data gets reclustered in some other fashion. It's pluggable. If you don't like the algorithm that we've implemented in the open source, you're welcome to actually contribute one more algorithm there. It's pretty fairly pluggable, and it's configurable, and it's incremental. So you don't need to recluster your entire data. We learned from some of the mistakes we've done in the past. We're trying to get better at this stuff. There's some tech stuff. It uses a space filling curve underneath, and it utilizes Z cubes for doing some of the incremental operations that happens. But pretty fun side of the code base. Highly welcome to actually check it out. It is super easy to use. This is the biggest feedback that we've heard from our customers, and it's also very easy to evolve. If you think you've made a mistake, it's super easy to just change the entire clustering thing, just move on with your business as usual. What we've observed is up to 7x faster writes compared to partitioning. If you have partitions, like millions of partitions, whatever, it's game over. For people who use Spark, you'll know that the job just hangs there, essentially sitting, like it won't finish. And from the read side, this is something that our team has focused quite a lot over the years in terms of getting this thing right, essentially, making sure the read performance out of the box is pretty fantastic. You've seen the announcement, Liquid has entered GA, and we've gotten some pretty fantastic responses from all the people who've used it. So if you've not tried it out, please try it out. Let us know, how you feel about it. We're more than happy to kind of work with you to improve this stuff, essentially. One thing, like, I know I was making a big deal out of that 4 exabytes number. I don't even know what to say for this 1.2 zettabytes. I had to look up what's the next one beyond exabytes. That's the amount of data that Liquid has helped skip for some of the existing customers, in fact. It's one of the most popular features that we've actually invested into in the recent times. The third challenge we were trying to solve was the ecosystem. What good is a format if no one adopts it? And if you make it super difficult for someone to adopt it, like, what are you going to get out of it, essentially? And that is the challenge that we took up. Like, a year and a half ago, we started interviewing hundreds of developers, and what's your biggest pain points around Delta? And the number one problem we found, let me motivate that. Delta has a fantastic connector ecosystem, don't get me wrong. And in fact, we've had a bunch of new players enter the town, despite it being a little bit harder to kind of get into. But the problem is, every time somebody writes a new connector, they would have like a different implementation of the Delta protocol, which is a big headache, right? You're an engine developer, you're an engine integrator. Why should you spend a lot of time trying to understand the Delta protocol details internally, in fact? So this is the problem that we've been trying to solve with the kernel project. The Delta kernel, think of it as a narrow waist set of libraries which you can use in order to integrate with Delta underneath. The idea being that now there are two personas. If you want to contribute a feature to Delta itself, come and contribute that in the kernel project. And the advantage of this is that anytime any of the engines upgrade the kernel, they pretty much end up getting your feature for free, essentially. There's really not much of a cognitive burden there. If you're an engine developer, things are super happy. You don't need to understand the protocol details anymore. It's just a very well set of APIs that are very well defined. You do the integration once. Maybe it's easy, maybe it's not. But once you do the integration, upgrade story becomes like super easy, essentially, subsequently. And that has been the theme that we've been going behind, which is, integrate once and leverage like the benefits throughout like every other engine, essentially. It's been having a very thriving ecosystem. We did not imagine we'll get here, but it's been a pretty fun ride so far. There's like a lot of new players in town that have started adding support for kernel, and it's a fun project. It's something that you can actively get involved today, essentially, if you're interested. There's a lot of work to be done, so if you want to collaborate with us in the open source, please come in. And the fourth and the final challenge is interoperability. We realize data formats are not a battle that is worth our time, essentially. It's so much of a pain for our users. Like, you spend lots and lots of time trying to make this decision of a FOMO, which is, what do I pick that will make me feel safe for the next 10 years of my life? It's a very difficult decision to kind of take. And that's why we set ourselves on solving this maze of MVCC matrix. Not this keynote, but last keynote. For those who've attended last year Michael's keynote, he used a very interesting analogy of MVCC, for those of you who don't know, is multi-version concurrency control. At its core, every single format implements some form of MVCC on top of Parquet. Parquet is the underlying data format. So a year ago, we were pretty much debating amongst ourselves, saying, why is it so hard to actually provide support for any other format? And that is how this project started, when we started looking at the entire fragmented lakehouse ecosystem, we would see that, okay, there is one ecosystem building around Delta, there's one more building around Iceberg, and the other one building around Hoodie. And that's how this idea of uniform came out to be, uniform, short for universal format. The idea was quite simple. Write once into Delta, that thing produces metadata for like the other systems, and you don't need to worry about using different connectors. Now you can use a native Iceberg connector to read into Delta, and you're good, essentially, all of a sudden. So it pretty much takes the problem from how do you choose between formats to why should you even choose any format? Just pick one, move on, essentially, with the entire thing. And our commitment, you've seen all the keynotes, is to work with the broader communities to make sure that this does not end up becoming a problem 2 years, 3 years from now, essentially. Uniform has also gone GA, pretty fantastic feedback so far. There's still a lot of investments that we're making here. We welcome you to give us feedback if you ended up using this one. That being said, now let me get to the beyond side of the talk. I'm very, very excited about Delta Lake 4. The work has just started. Like you would have seen, like one of the releases very soon. There's a lot of hard work that we'll have to put in over the next few months to make sure this stabilizes and whatnot. But I wanted to leave the stage with like one particular theme of Delta Lake 4.0. We want to focus on interoperability. We want to simplify everyone's life, and that's why we are here. But at the same time, we don't want to give you interoperability by compromising on stability. We want you to take Delta 4, deploy it in your production workloads without any lack of sleep or like losing sleep over it. And we will start enriching it with like next level features that are sure going to make you happy about it. So at this stage, I welcome TD to kind of walk you through what's in store for Delta 4.
Thank you, Rahul. Hey everyone, first of all, one round of applause for Rahul.
Thank you.
Thank you very much. Okay, I'm going to go a little bit more technical now. So Delta 4, the today morning Delta 4 preview came out, so you can kickstart these things, kick the tires of Delta 4. And the 4 features that we want to highlight as part of this preview, and those are 4 features I'm going to talk about, are things that we're very excited about because they're like fundamental architectural changes of how Delta and even Spark underneath operates. This is like taking something that is amazing to the next level, like really cutting edge. And so the 4 things I'm going to talk about is, let's start with Delta Connect. To really understand this feature, Delta Connect, we would first understand a crazy new thing going on in the Spark ecosystem called Spark Connect. Let me motivate this a little bit. I'm hoping most of you have used Spark. So think about how Spark runs. Spark has a driver and a bunch of executors. When you launch your Spark job, your business logic is actually running in the Spark driver. So that means that your application, let's see if this works. Yeah, so it actually works. So your application code is actually running inside the Spark's monolithic JVM process, which actually makes life a little bit complicated because that means there's a tight dependency between the monolithic driver and the application. Because if something goes wrong in the application, the entire Spark cluster dies. Or if something is wrong in the Spark cluster because let's say you upgrade it to the next version of Spark and there is some bug in the next version of Spark, your application dies. So there's a coupling between the fault. There's no fault isolation between your application and Spark. And so that leads to all sorts of complicated problems, like it's very hard to run IDs in your notebooks because if you kill your application, you kill the Spark driver. You cannot run Spark as a service that easily. You cannot integrate with other languages that easily. There is integrations with Python, PySpark, there is R, there is Go, but those are integrations at a very language-specific, half the things doesn't work, etc., that kind of level. So it's quite, the general JVM, other language interoperability is bad. So there has to be a better way. And we've learned this in the Spark ecosystem over the last, 14 years that Spark exists. And over the last couple of years, the Spark ecosystem has been understanding these problems, things that I talked about, and came up with a better way. That how to introduce an isolation between your application logic and the actual Spark driver server. And as with like many things in computer science, you need to have an interface. A clear, stable interface between the client side, which is your business logic, and the server side, which is Spark's own logic to actually execute your queries. So what happens is that this is a clear API. There is a Spark client library that your business logic compiles against. And at runtime, this is the following that happens. This is the API. There's a Spark client. When you write your application logic, what the Spark client does, it converts that application logic into the raw logical plans. This happens inside the scenes, so you don't need to really understand this. But this logical plan, the Spark client is actually pretty dumb. It's like a thin client. It doesn't really understand this. All it does is that it sends it to the Spark server that, oh, you figure out the rest. The Spark server takes that logical plan, and now the server has all this brains to really execute this. So it takes the logical plans, convert it to optimized plan, execution plan, the usual thing that happens in the Spark, generates the results, and sends back the results to your application. And that's ultimately what the application cares about, is I just want the results. I don't know how you execute it, I just want the results back. And so with this architecture, there's a clear isolation that your business logic is isolated from exactly what version of Spark is you're running on. If you want to use the latest version of Spark because it is faster, your application doesn't need to change, because as long as the next version of Spark follows the same Spark Connect client API, you can upgrade the server side without having your business recompile to latest version of Spark. So that eliminates a huge set of problems in the future. That is the next level architecture. But now for an external library like Delta to operate in this model, like for simple things like JSON that Spark natively understands, you don't need to change a thing between Spark 3 and Spark 4, where this is going to be much more robust. But for a complicated library like Delta that really goes into optimizing Spark, like specifying its own analyzer rules, optimizer rules, creating its own special logical plan, Delta needs to be re-architected in the same way, in this split client-server model, where the Delta client library works with the Spark client library to convert your Delta business logic into plans that get sent over, and then there's a Delta server library on the Spark server side which understands the Delta-specific plans, knows how to deal with it, works with the rest of Spark to actually execute and produce results. So that is a fundamental architecture change that is also happening in Delta, that we're splitting it into two libraries, and that will translate all the benefits that that Spark Connect was designed for to the Delta developers as well. Your Delta applications will be much more robust to changing Spark versions or Spark issues, etc. It will be a lot more easier to upgrade. It will be easier to debug because you can run Spark applications from your IDE, a Spark and Delta application, and it will talk to the server without leaving your IDE. So all sorts of benefits will happen. That's amazing feature number one. So you can see this is like a fundamental architectural change in how you deploy Spark and Delta applications. Second fundamental change is coordinate commits. Again, this needs a little bit of context. For those who are roughly familiar with Delta, this is like a tiny one-slide recap, is that Delta tables are a fully self-describing format where all the metadata of how to read the data is present in the file system itself. Like inside the directory, you have both the Delta log, which is the metadata, and the Delta log captures all the information of how to read the data files inside that directory. So it does not depend on catalogs, but it works absolutely great with catalogs because you just point the catalog to point to the storage location and everything else is self-describing. So the only requirement for Delta to operate in this pure file system way is that the file system must provide a mechanism for doing atomic writes to a file only if it is absent. That's how it updates the Delta log, that if there are two concurrent writers, only one of them should succeed in creating the next version in the Delta log. That's how Delta ensures that there is a linear history of all the transactions that has happened in the table. So only one writer should succeed to create version 2. The other writer sees that, oh, version 2 has already been created. It will reconcile the changes that it is proposing with the changes that were 1 and retry as version 3. So that's how it maintains linear history. But it requires that the file system ensures that only one of them can write version 2. Most modern file system actually supports this in one way or the other, except S3. So 3 years ago, we designed this alternate mechanism by which DynamoDB can be used as a coordinator to coordinate and linearize the writes before writing to S3. So instead of basically doing a conditional put inside the file system, you're going to do a conditional put inside DynamoDB. So in DynamoDB, you define what is the order of writes, and then once the order is decided, the actual metadata of the writes are actually synced to S3 in the same order that was decided. This is great. This works behind the scenes. You configure your cluster to actually use DynamoDB when you're using it on S3. Great. But there are a few limitations that we have learned over time. This relies on the user to have to configure the Spark cluster or any cluster, Flink or whatever. You need to configure it correctly. Otherwise, it will not use DynamoDB. It will just try writing to S3 and overwrite stuff, which is basically room for expensive mistakes. We shouldn't have to rely on you knowing the details and figuring out the right things as a user and stuff. That is not a good system. Second, stealing my own thunder. Second, it relies on, it is a more Spark-specific problem that you need to configure the entire Spark cluster to actually write in the same way. So even if you want to write a complicated application that writes to S3 and Azure and HDFS, that is not possible with this mechanism we designed 3 years ago. So we have learned on what is the right way to do this. That's what is coordinate commit is. Rather than the user specifying use DynamoDB, the log in Delta should specify that if you have to update me, you need to go through DynamoDB. And all the writers will see that information in the log that, oh, I need to use DynamoDB. The user doesn't need to configure. The system will automatically figure out, oh, DynamoDB needs to be used, otherwise I will not be able to write. So if writer 1 and writer 2 are new writers that are aware of this new feature coordinate commits, they will be able to commit, automatically will commit correctly. But the writer 3 that, let's say, is older, doesn't know about this, will not be allowed to commit in the first place. So this is correct out of the box, correct by definition. No room for user error. Benefit 1. Benefit 2 is that this coordinator doesn't have to be DynamoDB. It can be DynamoDB, it can be on any catalog, it can be file systems, anything that gives the ability to do the conditional puts and atomic guarantees and stuff. So you can basically, in your same application, mix tables which are coordinated in a different manner. So the application you write that I want to write to S3, Azure, and coordinated by some catalog like Unity catalog, which is open source now, all of that is possible because each table will tell you automatically how to write to me, and the system will figure itself out. But one thing to remember is that this does not eliminate file system. We have designed the system such that if you want to continue using file system, just like I want a directory, I don't need a catalog, I just want a directory, here is my ML workload, just point to a bunch of files and I just want to work with that, you can continue doing that. What this is extends the capability of Delta to new domains, so that new things are possible and also be correct out of the box. So that is a very important thing to keep in mind. Okay, moving on. The third and fourth feature, which kind of falls under roughly the same category of a major challenge Delta has been dealing with since day one, is how do you evolve the type and schema of a table to keep up with the changing semi-structured data that you may be ingesting. So keeping up, so imagine you're reading from Kafka or a bunch of JSON files or XML files, CSV, you have data coming in and maybe you wrote your application, your pipeline one day, you knew the schema, you coded it up, great. A year later, your schema has changed, like you need to add some new fields, you need to modify a few fields in data types of that. So these sort of problems occur when you have pipelines that are running across many years. And so over the last 5 years of seeing users run Delta pipelines, we have learned a bunch of things. And so that how do you evolve, keep up with your semi-structured data ingestion? So we started in delta 0.3 or 4 to attempt to solve this problem by doing the very simple thing. We are going to add new columns automatically. That is, we call it automatic schema evolution. We added support it in insert first, then it's added supported in merge. I think we were the first system to ever do something like this, that when you're writing, you can automatically simultaneously write data or merge data and evolve the schema by adding new columns. That was cutting edge 3 years ago. It works greatly on any arbitrary nested types. You have complex nested data within arrays, etc. It just all works out. But the problem is that over the years, your data type itself may change. Right now, when you add a column, the data type of that column is fixed when you added it. If that data type itself changes, that's a problem, and that can happen. For example, you chose your order ID to be int, 32-bit integer, but after your startup became successful and you're getting so many orders that 32-bit integer is not enough, you have to upgrade to 64-bit long. How do you do that? The only option right now is that you take the table and rewrite the entire table to, rewrite all the data that you have to a long type column, which is expensive. And it breaks all production jobs. You have to stop all jobs writing from this table, create the new table, rewrite everything to point to that. It's a mess. So that's why the solution is type widening. This is available as preview in Delta 4. And what it does is something very simple. It will, for a certain subset of types that can be automatically upcasted, like the example from int to long, you can automatically take whatever data is already written in a table as int, you can automatically upcast it to long without loss of data, loss of precision and stuff. So for these subset of types, what we do is that we allow the writers to upgrade the column type in this form from int to long. And then we have a table that is bunch of files are written from the past as int, bunch of files are written as long. The readers reconcile. The readers reconcile. At the time of reading, it'll say, oh, this is a file. Right now, the data type is long, but the file has int data. I'm going to just while reading the data, I'm just going to reconcile and automatically upcast it to long. And the new data, which is already in long, nothing needs to be done. So this can happen automatically under the covers. If you enable this particular feature, you enable auto schema evolution, and certain types, which are very safe to do, are automatically upgraded if you enable automatic schema evolution. And certain types you can enable explicitly, but in either of the cases, you don't have to rewrite all the existing data. The readers, if they're smart and support this feature, will automatically handle the automatic upcasting. That is only still solves a part of the problem, where you can upcast between a certain set of data types. What if you have this problem where, oh, I have a new supplier that is producing data instead of int order IDs or long order IDs, it's producing strings. And how do I handle that? The current way to handle that is, if you want that level of flexibility that it can be arbitrary types, you just write your data as a JSON encoded string in a string column. Then at the read time, you can do whatever parsing you want. You want to parse it as int, you want to parse it as string, everything is possible. But the problem is that you're doing all this data parsing, etc., on the read side, which is slow. So you're sacrificing performance for the flexibility in data types. With this new type variant, I think you heard about it in the keynote, the idea is that instead of storing it as a string column encoded as a JSON, you store the whole thing as this new column type called variant, where the data internally is stored in a much more efficient way that it makes it very, very efficient to parse your data out. Internally, even though the logical type is variant, internally, physically, in the Parquet file that Delta uses, you store the data as a binary encoded couple of columns. Now, I won't go into the details. You can look at the specification that is out in the Spark ecosystem for variant type. That's where the Spark is where variant type was proposed. But that makes it achieve the flexibility of storing as JSON, as well as the efficiency of storing it as raw, like standard Parquet columnar types, somewhere in the middle. So you're not making that massive sacrifice between flexibility and performance. So you can see that to use it is very simple. You just basically Spark, for example, as of Spark right now, but hopefully other engines will pick it up, it provides functions to take your data and put it and transform it into variant type. And there are functions to extract the fields inside that variant data, whatever you want at runtime. And and the performance can be drastically different. Like from JSON, if it is 1x, this can be 8x faster. So all of these are previewed in Delta 4.0 preview, which is built also on Spark 4.0 preview. So you can see that this is absolutely cutting edge. Spark is in preview, Delta for preview on top of Spark preview. This is absolutely cutting edge. Go kick the tires and give us the feedback. See what breaks, post GitHub issues, bug reports, etc. We are happy to hear from you. And the end, when we make a final 4.0 release of both Spark and Delta, we want these features to be amazing. So, and we need your help for kickstarting the tires for such experimental features. All right, I'm going to hand it back to Rahul.
Thank you, TD. Wasn't that fantastic? Like anyone excited about Delta 4? I guess like more hands raised, like awesome, awesome. Can I take a picture? Okay. Awesome. I'm going to tag all of you today. So thank you.
That's bright lights. Okay.
So we just touched the surface of Delta 4. There's like a lot of other tail features that are coming. We highly want to see all of you on the community channels. What TD covered today was just to kind of show you that this is the biggest release of Delta Lake so far. And he's touched upon a couple of things like variant and type widening to show you that there are some stellar features on the line. Touched upon Delta Connect to show you that we care a lot about stability. We want you to start upgrading things without really worrying about breaking anything. And he showed you coordinated commits to show you that we're committed to some of this interoperability, make sure that you're able to just have that peace of mind and not really worry about problems. So yeah, this is the graph right now, but we also want to make sure that we're continuously growing this thing. This is just merely a drop in the ocean of where we would like to kind of see Delta growing, in fact, and for that we need your help. And there's a lot of possibilities. You do not need to know Scala. You don't need to know like any specific thing. Delta's ecosystem is quite large. You're a Rust person, please come in. You're a Python person, please come in. If you just love using Delta, still come in, talk to us, and tell us what you like and what you don't like, and we'd be very much happy to kind of work with you. With that, thank you again for joining us today. It's been really, really fantastic having you here. Thanks.